Assalamu alaikum. So in the previous class we started sequence networks and equations, and we discussed uh, the transmission line, and we derived its sequence network and equation. Now we'll continue with that, and we'll derive the same network, that is sequence network and equation, for the synchronous machine. This is the equivalent circuit of a synchronous machine, a three-phase connected wire. Neutral is connected to ground through impedance Zn. This is the internal generated voltage EA, internal generated voltage EB, and internal generated voltage EC. And this is the self reactance or impedance of the synchronous machine, phase A, phase B, and phase C. So let's say it is loaded, and it supplies a current of IA from the phase A, IP from the phase B, and IC from the phase C. And the terminal voltage at phase A is VA, terminal voltage of phase B is VB, and terminal voltage of phase C is VC with respect to ground, not with respect to neutral, with respect to ground. So let us say this is the phase sequence EA, EB, and EC, and EA is leading to this EB 120 degree and EC EC by 140 degrees, 240 degrees. The phase sequence is A, B, and C clockwise. So we can write EA simply the same as EA. EB is A square EB. EB is A square EA. That is when we give a rotation of 240 degrees to EA, we get EB, and EC is E. This should be EA only. It should not be E square. It should be EA. You can change it. It is A times EA. EC should A times EA. So with this, we know that this A operator is 1 angle 120 degrees, and these are the three-phase balance voltages which are generated by the generator. So let us try first writing the equations of VA in terms of this, that is terminal voltage in terms of internal voltage, phase current, this impedance, neutral current, and neutral impedance. You can see it from here. If we start from here and go here, from this point to this point and to this point, T. So from here we can see EA will be equal to this voltage drop plus this voltage plus this voltage drop, that is this. So the same equation I have written over here, or we can see this VA will be this voltage minus this voltage drop and this voltage drop. The loop is, we write a KVL from this to this and then to this. This is the loop. So we can say that VA is equal to EA minus IAZS minus INZN. That is what I have written over here. VA is equal to EA minus IAZS minus INZN. We know that IN is the summation of the three currents, phasor summation of the three currents, IA plus IB plus IC. This is also depicted from here. You can see it from here. This IN will be equal to IA plus IB plus IC. I have shown it in the previous diagram, but the load is also in star connected. So replacing this IN by IA plus IB plus IC, we can simplify this equation. Then this IA, EA minus IAZS and IAZN, that is ZS plus Zn with IA minus Zn IB and minus Zn IC. Similarly for phase B, VB is equal to EB minus IB ZS minus IN Zn. This can also be shown from this loop. We can use the KVL in this loop. In that case, VB is equal to EB minus this voltage drop, that is IB ZS, and minus IN Zn. That is what I have written over here. Again, I will put IN is equal to IA plus IB plus IC and simplify it. It comes out to be this. VB is equal to EB minus Zn IA minus ZS plus Zn into IB minus Zn IC. Similarly, for phase C, it can be written as VC is equal to minus Zn IA minus Zn IB minus ZS plus Zn into IC. You can use the KVL in this loop. That is, now the KVL will be done in this loop. So VC will be equal to this EC minus IC ZC minus IN Zn. Then putting the value of this In, you can get this equation. Now I can give them the matrix form, that is VA, VB, VC, three equations, EA, EB, and this EC, and this is the third matrix, which is ZS plus Zn, 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 Zs plus Zn, similarly like this, and this will be IC, IB, and IA, IB, and IC. So these three equations, that is equation 1, 2, and 3, equation 1, 2, and equation 3 can be represented by this matrix, and this matrix can be represented, this column matrix can be written as VABC, that's what I have written over here. This column matrix EAEBEC can be represented by EABC, and this matrix, that is 3 cross 3 matrix, it can be represented by Z. So, and this matrix IAIB can be represented IABC, so that it becomes a compact equation, and it is very easy to write. After that, this we know that this VABC is equal to A times VA012. That means we can represent this voltage, the actual voltage, in terms of the sequence components. That is A times this 0, 1, 2, and we know that what is the value of A. I will still tell you what is the value of A. Similarly, EABC, that is this voltage, generated voltage, it might have its own sequence components, and to convert it into sequence component, we can use this A. EABC will be A times this EA012. Similarly, IABC can be written as A times IA012. So putting this value in this equation, that is 5, 6, and 7, and 4. So this will be A times VA012. This will be A times EA012 minus that remains as it is, and this IABC will be A into IA012. The same equation has been written over here. That means A VA012 is equal to A EA012 minus Z into A IA012. Re-multiplying A inverse, when we multiply A inverse to the whole equation, A inverse into A is identity matrix, that comes out to be 1, it comes out to be VA012. This also will be multiplied by A inverse, it will be also equal to EA012. Then this will be multiplied by A inverse, that is A inverse that A, it is to be multiplied by A inverse, and it remains as it is, IA012. I'll first complete this, that is A inverse that into A. A inverse, we know that is 1 by 3, 1, 1, 1, 1, 1, A into A square, not into, it's this element of this matrix, A square A. This is the value of Z, that is plus Zn, 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 that is plus Zn, 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 that is plus Zn, and A is A, sorry, 1, 1, 1, 1, 1, A square, A, and A square. I have told you the difference between A and A square is, we can interchange these A and A square and this A square, and we can put 1 by 3 in place of here, so it will be then A inverse. So when we multiply it and get the value, you will see it comes out to be, the multiplication of these three will be 3 times Zs plus 3 times Zn. This 3 is whole multiplication of this, or we can write it with 3 times Zs plus 9 times Zn. And the second element is 0, third element is 0, this element is 0, this is 3 times Zs, this is 0, this is 0, this is 0, this is 3 times Zs. Similarly, this, when we divide by 3, this 3 and 3 will cancel out, this 3 and 3 will cancel, and this 3 and 3 will cancel. It comes out to be Zs plus 3 times Zn. This is Zs, this is Zs. So we can represent this by Z012. It comes out to be this, where Z0 is equal to Zs plus 3 times Zn, Z1 is equal to Zs, and Z2 is equal to Zs. So I will write down the equation 8, that is this equation. We can represent this by Z012, so it becomes a little bit easy to write. So I write down the equations again. So this will be equal to VA0, VA1, VA2, EA0, EA1, EA2, Zs plus 3 times Zn, 0, 0, 0, Zs, 0, and like that, IA1, IA0, IA1, IA2. This can be also written as Z0, Z1, and Z2. So when the individual equations are derived from this matrix, we get VA0 is equal to EA0 minus IA0, Zs plus 3 times Zn, or VA0 is equal to EA0 minus IA0 Z0, where this whole term will be equal to Z0. Similarly, VA1 is equal to EA1 minus IA1 Z1, VA1 is equal to EA1 minus IA1 Z1. This is the same thing because ZS is equal to now Z1. VA2 is equal to EA2 minus IA2 ZS. You can write in terms of sequence impedance. VA2 is equal to EA2 minus IA2 Z2. Where Z0, that is this value, it is equal to ZS plus 3 times Zn, that is 0 sequence impedance. Z1 is equal to Zs, that is positive sequence impedance, and Z2 is equal to Zs, that is negative sequence impedance. Here we have not included the value of Zm, that is the mutual flux or mutual inductance between these two. If we take that mutual inductance into consideration also, the simple thing will be that then Z0 will be equal to Zs plus twice Zm plus 3 times Zn. Z1 will be equal to Zs minus Zm, and Z2 is equal to Zs minus Zm. That will be similar to that of the can say the transmission line. But I have omitted that, but you can include that as well if it is given like that. Now we have to calculate, or we can say we have to see where from this EA0, EA1 and EA2 will come and what will be their values. So I'll go to the basic structure of the synchronous machine. This is the stator, which is here driven in written in red. This is the phase A conductor, phase B conductor, phase C conductor. Actually it should have been A dash, B dash, C dash. So the current will be like this. I omit that because it makes the diagram a little bit complex. So for a generator, let us say this is the field and it is on the rotor. It rotates in this direction, that is anti-clockwise direction. You can see at this position the maximum voltage will be induced in phase A, and after it changes by an angle, or it rotates by an angle of 120 degree, maximum voltage will be induced in phase B. Similarly, when it rotates further by an angle of 120 degree, phase C will have the maximum induced voltage. We can see that first it will be A, and then B, and then it will be C. So that's what the phase sequence means. It means the order in which the maximum of the phases will appear with respect to time. So here the maximum will appear first for A, then B, and then C. So phase sequence for this case will be A, B, C. Same phase sequence is shown in the phasor form, because you can see that it rotates in this direction. All the phasors will rotate in this direction because phasors are rotating in nature. If someone sits on here, let's say at this dot, you can see that all the phasors will rotate. First it will see phase A, and then it will see phase B, and it will see phase C, because they will rotate like this. So that's how we can say this is the phase sequence. So its phase sequence will be A, B, C. Hence its phase sequence will be A, B, C, which we can conclude, we can see that this is the positive sequence phase. And since the voltage are also induced in the same manner, we can say that the voltage induced are the positive sequence voltages. Here the voltage induced are positive sequence voltages. Now negative sequence voltage means if we rotate in this direction, first the maximum peak will occur for this, and then the maximum peak will occur for this, and then the maximum peak will occur for this. In that case, the phase sequence will be ACB, but this is not the case in case of synchronous machine, because it will, since the rotation is in this direction, first peak will occur for A, and then it will be occurring for B, and then for C, because the direction is like this. So if the direction is in reverse direction, we can see in that case we have a negative phase sequence, but we don't have positive phase sequence. We can say that in this case, while we have assumed this rotation, and this is the positive rotation, the phase sequence or the voltage induced maximum is first for A, and then for B, and then for C. It is possible, but a negative phase sequence is not possible. So we can say that for a generator, it only generates the positive sequence voltage. Negative sequence voltage is not generated by the generator. The second thing is that zero sequence voltage are those voltages which are, let's say this is VA1, VA2, VA, so not. All the voltages have same values and are in phase. So here you can see that when this rotates, it is never possible that voltage A, voltage B, and voltage C will be in phase. The maximum will be in phase. Because you can see North Pole and South Pole are in different direction. When North Pole is directly directed to phase A, only then it will have a maximum. At that time, it will have some other value which is definitely less than maximum. Similarly, for this case, when it is directed towards A, it will have a other value of the voltage which is definitely, we can say, different from the maximum value. So we can say that the zero sequence voltage, or we can say the voltages at point A, B, and C will never be equal. So when they are not equal, we don't it means we don't get the zero sequence voltage at the terminals of the generator, or in general we can say that the zero sequence voltages are also not generated by the generator. So in nutshell, we can say zero sequence positive sequence voltage are generated by the voltage, but negative and zero sequence voltage are not generated by the generator. In other way around, we can say that if we have the same machine but operating as a motor, if we supply a positive sequence voltage to the stator of the synchronous motor or induction motor, so that, and the windings are placed uh, in space by, which are displaced by 120 degree in space, that we have shown over here. So now if we supply the three-phase voltage, positive sequence voltages, which are displaced from each other by 120 degree in time, to the stator with a voltage sequence A, B, C, the rotation of the rotor will follow A, B, and C. That means the rotation of the rotor will be in this direction. First, North Pole will point to A, then it will face B, and then it will face C. Positive sequence will be A, B, C, C, A, B, or B, C, A. In all the cases, it will be a positive sequence. Negative sequence will be A, C, B, C, B, A, or B, A, C. So the rotation of the rotor will follow A, B, C respectively, or rotation of the rotor produced by the currents will have the same direction. So what does this mean? The rotation and the torque produced by the currents will have the same. The rotation of this and the torque produced by the rotating MMF, or rotating EMF, sorry, rotating magnetic field will have the same direction. So this rotor will be rotated by the torque which is produced by the rotating magnetic field. So in that case, we can say that this is a positive sequence voltage. So for a negative sequence voltage, if we supply the negative sequence voltage to the stator of the sub-induced motor, the rotation of the rotor will follow ACB respectively, or in other words, we can see the rotation and the torque produced. Now the torque produced will be, because now ACB, the direction of the rotating magnetic field will be clockwise. It will be clockwise, and the rotation is in this direction. The direction will be opposite. It will oppose the actual direction, that is the positive direction of the rotor. If we supply the zero sequence voltage to the stator of the synchronous machine or synchronous motor, no torque will be produced, because to produce the torque, we should have the phase displacement in space and phase displacement in time also, because if we supply the same voltages which are in phase, in that case torque produced will be zero. You know this from the basics of synchronous machine. So we conclude here that for a synchronous generator, it generates only positive sequence voltage. It does not generate negative sequence and zero sequence voltage. Now we'll come back to this. So it means that positive generator voltage is EA, negative generator voltage will be zero, zero sequence generator voltage will also be zero. So our voltages, which we have written over here, this will be zero, this will be zero, this will be equal to EA, actual generator voltage. So VA naught will be equal to minus IA naught Z naught, that is zero sequence network equation. VA1 is equal to EA minus IA1 Z1, that is the positive sequence network equation. Similarly, VA2 is equal to IA2 Z2, that is the negative sequence network equation. Now these equations can be represented in terms of network also. Positive sequence network is this, where we have EA, that is the source voltage. When we this subtract a voltage drop from EA, we get VA1. That is, its circuit can be made like this. You can see EA, current IA1 is flowing through this circuit, and Z1 is the impedance. When this voltage drop is subtracted from this, we get VA1. Similarly, we don't have a voltage source in negative sequence network. We have only minus IA2 Z2. You can see VA2 will be equal to IA2 Z2 You can see the direction is from, this will be positive, this will be negative, and negative is at this point VA2 is positive, that means VA2 positive will VA2 will be minus IA2 Z2. Similarly, this VA naught will be equal to minus IA naught Z naught, minus IA naught Z naught. Here I have not shown you the effect of Zn, that is the neutral impedance. Okay, Z naught is here, the neutral impedance is included in this. So Z naught is not only Z, it will be equal to 3 times Z, and we can say that this Z naught will be Z naught is actually Zn is included in this Z naught. So the important thing from this is the three sequence networks are independent, and independency is given by this matrix. Because you can see that any equation does not contain any equation representing any sequence equation does not contain any other sequence equation. For example, if we have this sequence equation, that is, you will see only zeros, this 0, this 0, VA1, EA1, IA1, VA2, EA2. There is not, VA2 does not contain VA1 or VA2, VA0. VA1 does not contain VA0 or VA2. Similarly, VA0 does not contain VA1 or IA1 or VA2 or IA1 or IA2. So we can say they are again decoupled. Here also they are again decoupled. There is no voltage source in negative and zero sequence network. I have discussed this also. Only the positive sequence network has a voltage source, and I have told the reason for this also. The grounding impedance is reflected in the zero sequence network as Zn. The grounding impedance will be, or we can say, is connected in the zero sequence network as 3 times Zn. It reflects there as 3 times Zn, because Z0 is equal to Zs plus 3 times Zn. This was the sequence, because we actually want to find out the sequence network and equations for all equipments which we use in the power system. We have done it for the transmission line, we have done it for the generator, this synchronous generator. We will, in the next class inshallah, we'll do it for the transformers. Hope you understood. Thank you.